So I think a simple way to understand pressure volume work or how a chemical reaction can do work is to think about a piston and, for example, a car. And in a piston, in the car, we have fuel that's being reacted in the piston. Now this expanding gas that's in the piston is really our system. That chemical reaction, fuel plus oxygen, right, produces CO2 and water. This is our system. And so this system is actually doing work as it expands the volume of the gas that's inside the piston here. Now, it turns out that if you, and we call this PV work, it turns out that you can calculate the magnitude of the work that's done by the piston as work is equal to just P times V, and I put the magnitude bars here so that we don't worry about the sign. Now it turns out P delta V, it can be easily converted into joules using this conversion factor. 1 liter times an atmosphere is 101.3 joules. So, but here's the problem with this equation the way it is. It doesn't take into account that the fuel plus oxygen is losing energy. This is an exothermic process, and it is doing work as well. So it's losing energy and expanding against this force. There's a force that would be up here, right? It's connected to a crankshaft, and that crankshaft turns in response to the moving and the expanding of the gases in the piston. So this expands. Well, delta V would be positive if you go from a small volume to a large volume. And as a result, the sign of this equation has to be negative if you're taking into account that the chemical reaction is the system and it's losing energy as it does this work against this force, right? Does the expansion against a force. So the actual equation for work for gas reaction or change in volume against a pressure really is negative P delta V, and this takes into account the idea that the system is losing energy as it expands against that force. Okay, so let's go ahead and I wanted to show you quickly how you could calculate the amount of work that is done by an expanding gas. So it says, how much work do you expend when you blow up a balloon to 12 liters, and that's pretty big, at 1.10 atmospheres. So you have to think about the equation, right? You're the system. How much work do you expend? So we're talking about you being the system. So W for you is equal to negative P delta V. Now, my delta V is 12 liters. And my pressure is 1.10 atmospheres. So this is what happens. You'll say work is equal to negative P delta V. That's going to be negative 1.10 ATM times 12.0 liters. Now, this isn't joules, and we typically want to do this calculation in joules, and what you'll use is the conversion factor that I showed you here, that 101.3 joules is equal to 1 atmosphere times a liter. So I'm going to go 1 atmosphere times a liter is 101.3 joules. Okay, so what that gives us then is this will cancel like this, right? And then I'll end up getting 1,337 joules, or with two significant figures, 1.3 times 10 to the third joules, or 1.3 kilojoules, since this is a direct substitution like that. Okay, so that's the amount of energy that you lose when you blow up a big balloon, about 1.3 kilojoules. Again, you're doing the work to expand, right, the volume of air in the balloon by 12 liters, and so you lose that much energy. Oh, sorry, I left the negative signs out down here. So we're at the point where we can talk a little bit about delta E, internal energy changes, and heat and work for a system. Okay, so as it turns out, we've talked about delta E being a state function, that the change in energy, right, only depends on the the final state and the initial state. So think about when you're driving a car, right? The amount of gasoline that you use would be the change in the internal energy of the car. That's the total energy that you have. So I'm here. Oops, sorry. This is where I'm at here. This is Reedley, okay? And I'm going to drive to Fresno. Now, I drive slow. Okay, so let's say I'm going from Reedley to Fresno and I'm a slow driver and I don't accelerate very hard, right? What does that tell you about my gas mileage, right? Everybody kind of knows this, but if you drive more easily, you don't accelerate hard, and you drive a little bit slower, your gas mileage will be higher. So I'll get more out of the internal energy of my car, the gasoline energy, right, than somebody who drives fast, like, say, my wife, who likes to drive fast and likes to accelerate hard. So now, because we're going the same distance from Reedley to Fresno, right, what's ending up happening is that because I drive slowly, right, I generate less heat in my engine. That's the Q. So I can get more work out of my engine for the same change in internal energy. On the other hand, if you drive fast, right, then what ends up happening is you get less work out of your system because you're going to be generating more heat. Now think about that, right? You won't be able to drive as far on a gallon of gas because the part of the work is getting you to the point where you need to get. So you end up spending more internal energy, more gas. Your gas mileage goes down. So having said that, right, what that means is these two, Q and W, turn out not to be state functions. State functions can't depend on how you did it, okay? But now here's the deal. The change of internal energy, right, will always be a state function. So even though Q and W aren't state functions, when you add them together, conservation of energy says that has to be the change of the internal energy of the system, okay? Now, I was going to point out one other thing about state functions and non-state functions in science in general. Generally speaking, the way you can tell a state function, this sounds silly, but it's very helpful for some people. Uh, all the letters that are capitalized in science are generally state functions, and a lot of things that aren't state functions are written in lowercase letters. It's just a designation. I don't know if it's intentional, to be honest with you, but that's just the way it has been in my experience. So Q and W are not state functions. Now, for a chemical reaction, we're not talking about a car engine now, but we're just talking about chemical reactions. The system and surrounding exchange energy two ways. One is through heat, which we often measure through the MCAT equation, and the other is through work, which we measure in terms of P delta V, or negative P delta V, if you want to have the full equation in there. So heat and work are the ways in which energy is exchanged between the system and the surroundings. Heat is not a state function. Work is not a state function, but the two combined happen to be a state function which describe the internal energy change in a reaction. So how do you have to use this information, right? So here's just a quick type of calculation you might be expected to do, or at least understand in terms of fundamentals of exchange of energy. It says, what is delta E if a system releases 325 joules of heat while expanding by 3.53 liters against a pressure of 2.5 atmospheres? Okay, so let's break this down. I want to know delta E. And I know that's Q plus W. So if it says the system is releasing 325 joules of heat energy, that means my Q is negative 325 joules. That's the energy lost by the chemical reaction. Now, when it says it's expanding, right? W is equal to negative P delta V. So I'm going to have 2.50 atmospheres, or negative, times an expansion, which is a positive delta V. So my delta V is 3.53 liters. So this will just be 3.53 liters. And again, it's 101.3 joules per liter times atmosphere, like that. And these will cancel like that. And we can calculate that value as being negative 893.98 97 joules. My eraser decided to stop working. I guess it worked and didn't do anything. Okay, joules. So finally, we can calculate delta E. That's going to be minus 325 joules plus a negative 893.9 joules. That'll come out to be negative 1,218.97 joules, and I believe we have significant figures to the ones place, so that'll end up being 1,219 joules, or 1.219 kilojoules, like that. Negative, sorry, I forgot the negative sign. That's the amount of energy then that is lost by the system as it releases energy and expands against the pressure of 2.5 atmospheres. And just for clarification, right, that could be a piston and a chemical reaction in a piston where the piston is pushing against a pressure of 2.5 atmospheres. But it could be chemical reaction that's doing that, a different kind of chemical reaction. It could just be gas being injected into a piston, that kind of stuff.